Let's discuss this question here. At an amusement park, there is a rotating cylinder ride. So after reaching a certain speed, the floor falls away, leaving the rider plastered against the wall as shown in the figure above. Well, this figure is definitely not clear enough to understand what does a rotating cylinder ride means. Okay, but you know that the rotating cylinder will be rotating at a certain speed. Then once it reached that certain speed, the floor where the person plastered against the wall is standing on will falls away. Okay, so the platform where the person is standing on will drop, but you will see that the person will remain on the wall without falling along with the platform. Okay, and they say that the radius of a cylinder is 4 meter and the speed of the wall is 8 meter per second. Let me do a bit of labeling here. So the radius of the cylinder is towards the center. This one has a distance of 4.0 meter, and the speed of the wall, okay, you can see that the wall, their speed over here, okay, will be equals to 8 meter per second. Okay, so they ask you to draw a free body diagram of the rider. Okay, but before we do all the sketching, let's actually go and watch one video to look at how does a rotating cylinder ride works, because not everyone been on one before, right? Okay, so this is a video provided by this channel, the Red Coaster channel. Shout out to them. And this is a video showing Roto Luna Park Sydney 2020 point of view on ride. Okay, so let's look at how this rotating cylinder ride works. Okay, so initially you can see that the persons are all standing plastered against the wall. They are leaning against the wall. Then you can see that at some point they will start to rotate the whole cylinder over here. This is the whole cylinder. You are seeing a view inside the cylinder, and as time goes on they will start to rotate the cylinder. Yes, okay, so you see that the surrounding, you can see that it's rotating, right? It's actually the cylinder that is rotating right now. So the person are standing inside the cylinder, leaning against the wall, and the cylinder is rotating. Okay, so they're all relaxed right now, nothing really happened, but observe the ground. Okay, right now they are standing on the platform over here. Okay, but in a few seconds you see that something will start to happen. Once they achieve a certain speed fast enough, then you will see that, okay, let's give it a bit of time. Observe the platform. Okay, this kid over here definitely look quite nervous. Okay, it's about right now. Okay. Okay, do you see that the platform leaves? The platform falls away. I can see that all the uh all the riders of this ride over here, they are all still plastered against the wall, but they are not falling to the ground. They are supposed to fall towards the ground, but because of the rotating effect, somehow these people over here still remain plastered on the wall without falling to the ground. Okay, and the idea is you must plaster against the wall, or else you'll be falling to the ground. Okay, so after the ride is finished, you can see that be around now maybe. Okay, the platform will start to rise back to the ground, or they will be asked to go try to move to the ground. Okay, so that's the end of the ride. We fall back onto the platform. Okay, so this is a rotating cylinder, right? So I hope you have a clear idea how does this work already right now. Okay, so the cylinder will be reaching a certain speed, then the floor will fall away, just like what we see just now, but the rider will still plastered against the wall. Okay, so I think we are clear the situation. The video I think show everything that I want to explain. Let's try to draw a free body diagram of the rider over here, and we'll be drawing the free body diagram for the rider when the rider is at this position over here. Okay, so this dot over here will be representing the rider. So of course, if we sketch our free body diagram, we know that the rider has mass, therefore the rider will have weight. So this is the weight of the rider. Continue. The rider is not attached to any strings, ropes, or cable, so there's no tension for this situation over here. And is there any force explicitly mentioned in the question? They don't mention that you have any force that a human pushing the cylinder or the human pushing on the human or on this rider over here. There's nothing such being mentioned, so there's no external force. Next, is there any contact surface or not? Yes, the person over here is definitely sticking onto this wall over here, and because this is a contact surface, you should expect that the cylinder will be exerting a normal force on this rider over here. So because this is a normal force, the normal force should be perpendicular to the surface. So the surface is vertical, the normal force will have to be horizontal. The normal force is horizontal, and to know that where it's pointing to the left or to the right, remember the keyword push. The cylinder will be pushing on the rider. So to push on the rider, the cylinder will be pushing to the right. I'm talking about the rider when the rider is on the left hand side of the cylinder. If the rider is on the right hand side of the cylinder, then the wall will be pushing to the left. Okay, so but for this case, we are sketching a free body diagram when the rider is on the left hand side of the cylinder. So therefore, the normal force will be pointing to the right. Okay, so what is supporting the, if we leave our free body diagram like this, then of course the rider will be falling to the platform. When the platform falls off, the rider should be falling along with it because there's no net force. The net force in the y-axis is pointing downwards. But that's not the case. What allows the riders to stay plastered on the wall without sliding downwards? It's because there's friction as well. Okay, you remember that this is a rough surface as well. So there should be a friction trying to balance the weight over here in order to prevent this person from sliding downwards. Okay. So again, there's no sliding that occurs. So this is a static friction. Okay. So now they ask you to calculate the minimum coefficient of static friction that must exist between the rider's back and the wall if the rider is to remain in place when the floor drops away. The minimum coefficient of static friction. Okay, this is very rare. We seldom ask for minimum, we usually ask for maximum. But this one asks for the minimum static friction required so that the rider's back and the wall is to remain in place. There's no sliding, so the rider will not fall onto the platform. Okay, so again, we are going to analyze the free body diagram. You already see that there's nothing to be resolved over here. So we'll analyze the x and y axis. For the x-axis, you know that rotation is happening like this. This is a horizontal circular motion. So definitely there's circular motion in this axis. So it is not in equilibrium. So therefore, you're going to analyze it using sum of fx equals to mass times the centripetal acceleration. Okay, for the y-axis, you want the rider to remain in place. You don't want it to slide down to the floor. Definitely will not be sliding upwards. So therefore, it will be at rest in this axis. We can call it to be in equilibrium. That's why sum of Fy equals to 0. Okay, so we pick our equation already. We are done with step 3. We move on to step 4 where we start to do our calculation. So for the x-axis, sum of fx is equals to mass times the centripetal acceleration. Okay, so I'll be changing it to mv squared over r. Why am I changing it to mv squared over r? It's because they provide us with the speed of the wall moving at 8 meters per second, right? So that's the linear speed of the rotating cylinder. So that will be the linear speed of the rider undergoing circular motion as well. Okay, to be more specific, this rider here will be moving in a circular motion, and this rider here, it has a linear speed of 8 meters per second as well. Okay, so that is the speed of the wall, also the speed of the circular motion of the rider. Okay, on the left hand side of the equation, we need to put in the force that is acting in x-axis. Oh, I forgot to label the direction of the centripetal acceleration. It should be pointing towards the center of the circular path. Okay, so in this case, the force that is pointing in the same direction will be the normal. So in that case, normal will be equals to mv squared over r. Okay, so again, normal we have to take it from the y-axis probably. Okay, we need to relate to the y-axis. y-axis is equal to 0, so we take the static friction minus the weight of the person equals to 0. So know that the static friction will be equals to the mass of the rider multiplied by the acceleration due to gravity. Okay, right now at this point, how should we move forward? We know that static friction will be related to the normal force through this equation over here. When the maximum static friction is achieved, it will be equals to the coefficient of static friction multiplied by the normal force. This is when the static friction is maximum. So this is for situation when the static friction is maximum. Okay, so when the static friction is maximum, you might be thinking that then in that case the coefficient of static friction will be maximum as well. But they're asking for minimum coefficient of static friction. So why is it maximum static friction but minimum coefficient of static friction? Okay, to explain this is a bit complicated. I will try to do it. Okay, but let's try to finish the question first. Then after that, I'll explain how does it work. Why is it minimum coefficient of static friction? Okay, let's open this up to become mu s multiplied by the normal force equals to mg. So now the normal can be replaced by mg divided by the coefficient of static friction. Okay, you replace the normal with mg divided by the coefficient of static friction, and that will be equals to mv squared over r. You can count the mass over here, and what are they asking for is the minimum coefficient of static friction. So static friction should be on this side, the rest should go to the other side, so that will be gr over v squared. Okay, so you can do your substitution. 9.81 times the radius, which is 4.00, that's the radius of the rotating cylinder, divided by the linear speed, which is 8 meter per second. So you can get the answer of 0.613. Now, to explain that why is this value over here the minimum coefficient of static friction, let's look at this equation over here. Okay, the purpose that we have minimum coefficient of static friction between the rider's back and the wall is to make sure the riders remain in place, right? So for the rider to remain in place, sum of Fy will be equals to 0. If the sum of Fy is not equal to 0, that means there will be an acceleration in the y-axis. Either the object will be accelerating upwards or accelerating downwards. But our purpose here is to make sure the rider remain in place. So we must make sure that the sum of Fy is equal to 0. Okay, the sum of Fy will be a combination of the static friction and the weight. To be more precise, the static friction pointing upwards will need to balance the weight pointing downwards in order to have a sum of Fy equals to 0. Okay, we know that the weight is fixed already. So that means the static friction that you need for the rider to remain in place is fixed already, and the static friction required will be equals to the weight. The magnitude of the static friction required will be equals to the weight, so that when they are pointing in opposite direction, they can cancel each other out. Sum of Fy is equals to 0. Okay, so you know that your static friction will have to be equals to the weight, but you know that static friction actually depends on the normal force and also the coefficient of static friction. So the idea is like this. This static friction here is related to the normal force, that one we know. And because the rotating cylinder is rotating at a speed which is fixed already, then therefore the centripetal acceleration that is required for the object to be moving in uniform circular motion is fixed. You already fixed the speed already, so the v is fixed, the r is fixed, so the centripetal acceleration is fixed already. So that means the normal force that is required to sustain this ride, there's a fixed value already. You cannot have value great. The normal force that you required cannot be greater than this amount, cannot be less than this amount in order to sustain this centripetal acceleration. So this normal force is fixed already. That means in order for the static friction to be equals to the weight, your coefficient of static friction will have to have a minimum amount of 0.613. If your coefficient of static friction goes below 0.613, then mu s multiplied by n, which is the maximum static friction, will be less than mg already. Okay, again, if your coefficient of static friction is less than 0.613, then less than 0.613 multiplied by the normal that is fixed because you have a fixed speed for the ride already, will be less than the static friction requires to balance the weight. In that case, the weight will be overpowering the static friction, then the rider will be sliding downwards. Okay, if you go beyond 0.613, it's still okay. Why is it still okay? Then that means that this value greater than 0.613 multiplied by the normal, which is a fixed value, be greater than the mg over here, right? If your value over here is greater than 0.613, then greater than 0.613 multiplied by normal will be greater than mg. That means what? That means by your friction, your static friction here, still haven't achieved its maximum static friction yet. Okay, it's still a static friction, but your static friction can be greater than that. It's still not the maximum. So your static friction at this point will balance the weight, just that it is still haven't achieved its maximum yet. So technically, what does it mean is, if your coefficient of static friction is greater than 0.613, then this is not Fs max. This is just a regular Fs. It's just a regular static friction. You still haven't achieved its maximum. Okay, but still the static friction will be countering this weight over here, making the sum of Fy equals to 0. Okay, you need to have a strong idea of what is static friction first, because static friction, right, the magnitude can vary. There's a maximum that you can achieve, and the maximum is calculated by mu s n, but you can go below that. Okay, the way to determine the magnitude of static friction is to use Newton's first law, which is Newton's first law over here. Okay, you know that the static friction is there because it wants to cancel out all the forces in the opposite side so that the net force equals to 0. So if it is right, if this wall over here has a static friction that is greater than 0.613, what happens is you will still have a friction. It's just that the friction is not the maximum of a maximum static friction that the pair of surface can generate. It's less than that, but it's still static friction and still able to balance the weight over here, and the object still able to remain in place. So your coefficient of static friction can be greater than this amount 0.613, but it cannot go below 0.613, because if it goes below 0.613, then this multiplied value over here will be less than the weight already. Okay, the maximum is less than the weight. You cannot go over the maximum. So no, you know for sure that the weight will be overpowering the static friction, because the maximum is achieved already. You cannot go beyond that, but it's still smaller than the weight. So the weight will overpower static friction, causing the rider to slide downwards. So you cannot go below, you can go beyond. So that's why this is the minimum coefficient of static friction. Okay, you can re-listen to this explanation a few times to get it. But I think that wraps up our discussion for this question over here.